Good evening.
Good evening, ma'am. Okay, good evening, everyone. I hope you all are fine.
Yes.
Okay, good to see and welcome to the next session, assignment number 9 on the course of engineering hydrology. I'm presenting my screen. Kindly let me know whether my screen is visible to you as well
Yeah,
as
it's visible.
I'm audible to you also. Am I audible to you?
Yes, yes, you are audible.
Okay, good. Okay, so in this session, we are going to discuss about the problems related to unit hydrograph of different durations. We will also look into the topic instantaneous unit hydrograph. Then there are certain models based on hydrologic as well as hydraulic routing. So we will also look into this, that what are the principles and what are the assumptions involved in selection of these hydrological as well as hydraulic model. Then there will be certain numericals related to instantaneous unit hydrograph. We will also discuss one of the famous method for developing the unit hydrograph for ungauged catchment, that is Snyder's synthetic unit hydrograph. So with this brief introduction, I'm going to directly to the problems. So today's discussion will be more towards the numerical part compared to the conceptual questions. Here we start with the problem related to conceptual question only. So the question here related to unit hydrograph. So you can see the question here. The unit hydrograph can be used to derive the hydrograph resulting from any amount of excess rainfall, right? So this question is asking about the assumption, like we can derive the unit hydrograph. Definitely we know that if we are having the coordinates of direct runoff hydrograph, as well as if we have an idea of effective rainfall, that how much effective rainfall is there in certain duration, so we can directly derive the unit hydrograph. But we already in the previous session itself we have discussed that there are certain assumptions which are associated to the concept of unit hydrograph. So here again the question is the same. So for developing this simple linear model, there will be some certain assumptions. Now you have to tell them. So the options are as follows. The excess rainfall is uniformly distributed. Try to focus on the keywords, okay?
Yeah,
So
it's
here
correct.
one keyword is like uniformly distributed over the whole drainage area. Then the second option is the ordinates of all DRH of a common base time are directly proportional. Again, look at the keywords. I'm keep reminding you. Then the third one is for a given watershed, hydrograph resulting from a given excess rainfall will be remain unchanged. And the option at last, it is about all the correct. I want everyone to answer this.
All are correct.
Okay, all are correct from your side. Then I want others to answer.
All are correct.
All are correct. Okay, good, ma'am. Then
Balamurugan
proceed.
also in the same line. All are
Okay,
correct.
that's good. So yes, you all are correct. Definitely, what are the assumptions like A, B, and C? They all are the part of assumptions taken in deriving the unit hydrograph. So for your information, I just added the slide to further describe the assumptions. So linear hypothesis, we already know that it is based on the principle of proportionality and superposition. Then the time invariance, that means whatever the characteristics are there with the time as well as catchment characteristics, they are going to remain unchanged. Okay, keep in mind that whenever we are using the unit hydrograph kind of concept, uh, in case of field oriented work, what we did, we usually assume that unit hydrograph will remain unchanged for a period of maybe 5 to 6 years only. Maximum we used to take this much of year. Then again, after this much of period, we have to revise this. Okay, we have to revise the unit hydrograph. We have to see there may be certain changes with regards to catchment characteristics, like there may be possibility that geomorphology of the region may get changed, or even the size, or maybe you can say land cover pattern, or the soil distribution texture may be changed. So these kind of stuff may have changed within a period of 5 to 6 years, then definitely we have to revise that. So again, the related to effective rainfall, so it should occur uniformly over the entire drainage area, we have already discussed. Then again, the point related to unchanged characteristics of the catchment, Okay, and then it also assumes that there won't be any kind of storage component, like there won't be any kind of depressions or losses will be there. Okay, now moving to the next question here. So the question is related to bit, you can say, a step response function. So you can answer this question then only if you have an idea that how step response functions is plotted. Okay, so in the previous discussion itself we have tried to look upon two major response functions. One was what? That was an impulse function. Okay, and then another one was what? That was a step response function. Step response function. Can anyone tell me what are the relation between both of them? We have come up with the while we were solving one of the problem, we tried to look upon the relation between them. Do anyone remember what was the relation? Okay, wait a minute. Someone is trying to join. Okay, Bala Murgan is joining. Okay, good. Yes. If anyone can answer that, we in the previous discussion we have noticed one problem which were defining the relation between these two functions, that is impulse function as well as the step response function. And you also you may be knowing that while deriving the step response function we were using the convolution principle. Okay, so convolution principle is just a kind of integral principle. We are integrating a certain factor, you can say a function, okay, in order to derive the step response function. So it was an integral, like if we want to derive the step response function, okay, so step response function will be an integral of impulse function.
Response
Okay.
function.
Yes, so we have discussed this in our previous. So what I want to say is that if you take an integral of certain kind of impulse in the sense what, can you have an idea that impulse is in the sense what, like for a a small change in the interval of time t,
Yes.
there is a possibility that I'm saying that intensity of the rainfall is coming, okay, and it is coming and it is going away, like you can say t1 in the sense of 0.000 something, okay, it will be a 7, you can say, and then again in the figure of 3 decimals only I'm taking, and from 7 to it is going 9. Now the precipitation came and it went away. So you can say that yes, of course, that this change in the interval of time is very very small, but yes, what we got a certain kind of function. Okay, so this function could be assumed as a impulse. It is creating some effect in the watershed. Okay, like by assuming a small interval of time. So definitely while we are plotting we are getting a certain kind of impulse. It come and it went away, in the y-axis I can take an intensity. Okay, intensity I'm taking, and here you can say you can take a t value. Then I'm just saying that this is a first what I will say a kind of event. Okay, so event 1 is there, you got the impulse. Now again event 2 happens again, and you are now again getting a certain kind of impulse. Now I want to integrate it. Okay, I want a cumulative effect of both of them. So for that case I need to take an integral, so it will draw a certain kind of smooth curve. If we are taking a integral of that, integral of these impulse, we will be getting certain kind of smoothened curve, and this smooth curve will be taken as a step response function. Got it? Now from these options, can anyone tell me which graph you are aware that we can have some kind of smoothen curve? Okay, a kind of curve we are getting, a kind of curve. A kind of curve in the sense, yes, definitely. If you are talking about the hydrograph, then of course it will be a rising as well as the falling limb, both. Okay, in all the cases like D as well as C, and instantaneous unit hydrograph. But if I talk about S curve, so S curve will get like
Static.
it will be a straightened down after a certain
Straight.
interval of time. So
Yes.
basically this step response function represent as hydrograph only, getting cumulatively added, and at the end it will get constant. Okay, so just for your information, so if you talk about the impulse response function, so it is receiving a unit impulse in the sense you can take any parameter, like I am saying rainfall, I am saying intensity, you can take any parameter. Okay, and now if this is you can see there is a one impulse which is coming in a particular catchment. So impulse is coming into the system is nothing, it is, you can assume it as a catchment. So impulse is coming and then we are getting some kind of output. Okay, so impulse response function is derived like this graph, you can see. Now what we are doing, unit response, if you talk about unit step response function, so if we take the integral of unit impulse, we can get a curve like this, a smooth curve like this, and it will get constant at after certain period of time. So it can be regarded as a shape like S hydrograph, right? Is it clear to all?
Yes.
Okay. Okay, moving to the next question. So different synthetic unit hydrograph are derived based on. So synthetic unit hydrograph. Before moving to this, I just want your opinion about this hydrograph. Synthetic unit hydrograph, what is its application?
I
Why
think
this?
dimensionless unit hydrograph.
Yes, of course, it's a dimensionless unit hydrograph. I just want to know its application, like where this kind of hydrograph is useful, where we can use this, because this is one of the most you can say widely used hydrograph. Do anyone knows the application of this, where it is suitable?
In ungauged catchments.
Yes, right, ma'am. So the thing is, wherever we are facing scarce region, data scarce region, okay, like you can say in any catchment we don't have any kind of meteorological stations, or maybe stream gauging stations are not there, but still we want to predict the hydrograph kind of like we want to predict the hydrograph in this region without having and meteorological, or I can say hydrological data. We don't have a hydrological data, but yes, we have idea about its catchment characteristics, or you can say catchment properties we know. Knowing the catchment properties, we want to derive the expected unit hydrograph, or unit hydrograph which can occur if any kind of a stream is flowing here. So we can predict here. So that is why synthetic unit hydrograph is important, because if like if we don't have a data, then also we can achieve in plotting the unit hydrograph. What additional and necessary data is needed is that we know some hydrological information which is just nearby to this region. Like there will be a certain kind of catchment which is having some similar properties with this one. Then only we can derive the unit hydrograph. So the condition here is what? We want to have catchment characteristics same, and also we should have some idea about hydrological parameters in the known catchment, and then we can derive this. So these are the things. Now I want you to answer this. Different synthetic unit hydrograph are derived based on. So there are assumptions. Just I discussed that there are some similarities, okay, that we have to take in mind before using the synthetic unit hydrograph. So you should have an idea what are those options. Ashish, you were saying some option.
Yeah, B is, I think B is also correct.
Okay, so you are saying geomorphological characteristics and hydrograph characteristics, right? So geomorphology, in the sense there may be a possibility that drainage density, or maybe whatever the stream is flowing, it may have changed its path over the time. So yes, these information is necessary for this. And then from the word itself you can say hydrograph characteristic. Yes, so we should have some idea, known parameters of the flow as well as rainfall, and also the relation between rainfall and runoff. We should have idea in the known catchment, and then we can go for deriving a unit hydrograph on an ungauged catchment. Then okay, one more thing I want to say, that watershed characteristics should be same. Okay, these characteristics should be same. Watershed characteristics means it will cover the slope, it will take account of parameter, then there will be a size, you can say, and then there could be a parameter related to area. Okay, so these parameters should be considered. And then yes, C option is also correct, it's a dimensionless unit hydrograph. And then model of the catchment storage, there are certain models which can directly predict the response. So this option is also correct, we are looking into it. So if we want to derive a synthetic unit hydrograph, so we can come up with a unit hydrograph. Okay, we can derive it. How? Why it is important? So in order to have a unit hydrograph for other locations on the stream in the same watershed, okay, I am saying that I am having a gauge station at this point, and I got all like whatever the information, or maybe you can say unit hydrograph, I got it from here. Now I want the same prediction, like whatever the unit hydrograph I have predicted here, but here station is not here, like we don't have any kind of station at the outlet, but still we want to know that what would be the scenario of unit hydrograph. So using this method we can predict without having any kind of gauging station. Also there is a one more like condition, you can say, for nearby watershed of a similar characteristic should be same. Now this synthetic unit hydrograph can be derived in three major aspects. Okay, so first one is what? If we are selecting a water characteristics, so watershed characteristics in the sense what? Geomorphological characteristics I want. So area, length of the stream, we have this idea, we have the information regarding this. Then hydrograph characteristics, we also have the idea, peak, flow, rate, base time, I have these information. with me. Then using this method, Snyder synthetic unit hydrograph. Okay, Snyder is a famous person who have given a his own model to derive a unit hydrograph. So there are certain empirical equations are he has given. Okay, and then again a Gray's method is also there. Then if we are selecting a dimensionless unit hydrograph, so using this particular method we can also get the unit hydrograph. And what is its method? So SCS dimensionless synthetic unit hydrograph method is there. Then another criteria for deriving the unit hydrograph is that using the models. So models in the sense what? Nash model is there, Clark's model is there. They can directly give you the unit hydrograph. What you need is that you have to give the inputs. Inputs in the sense what? You already know that we need some hydrological parameters, as well as we should have some information regarding the watershed characteristics. Okay, moving to the next question. The width of synthetic unit hydrograph are distributed with respect to the peak as. If we are having a synthetic hydrograph like this, and if I plot up like I'm assuming it as symmetry, and there will be a certain kind of peak. Okay, so Q peak will be here. Now what is it asking? It is saying that the width of synthetic unit hydrograph. So this is a unit hydrograph. So it will be having a certain kind of width in the sense this one, but this is the maximum width, and we used to call this this width as what?
Time base.
Yes.
Base period.
Base period, right?
Yeah.
Base time or base period. So this is the maximum value. But while we are dealing with the synthetic unit hydrograph, we also need some information like width at 50% of QP. 50% in the sense maximum, 50% in the sense half of the maximum discharge. Then while we are deriving, we are making a synthetic unit hydrograph, we should also have idea that what could be the discharge at like 70, what would be the width at 75% of maximum discharge, that is QP. So these widths should be known to us, but here the question is somewhat different. Question it is saying that with respect to the peak, how the width are divided. So this is our peak coordinate, you can say. Now it is asking about the area, that how much this area and how much this area. So it is asking about the area. So options you can see 1/3 of the width are distributed before the peak. So if I am assuming that base period is written as B, so for the first part, this is first, this is second. So first it is saying that this width, this entire width from the symmetrical line which I have plotted in between, that is the ordinate of the peak. So from that point to the origin, it is saying that it will be 1/3 of the width are distributed before the peak. In the sense it will be a B/3. Am I right? This option is saying like this, na? And
Yeah,
then
correct.
if I am taking the other part, so other part will be what? It will be 2/3 of B. So the questions are based on that only. 1/3 of the width are distributed before the peak. So first one, if you are selecting it as before the peak, so it will be B/3. It is saying like that. Then 2/3 of the width are distributed before
After the peak.
What?
A and D.
A and
D.
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 Okay. B.
D. 2/3 after the peak.
Okay, after the peak. Yes. Okay. So you are right. Yes. So for the first part, width is divided in 1 by 3rd, and then after the peak it will be 2 by 3. So how we have come up? So this is just for your information only. So width of the unit hydrograph in hours, you can see just I mentioned in the graph itself that there could be a width like W50 for representing the 50% of the peak discharge, and then there will be W75. These widths will be required while we are about to make a synthetic unit hydrograph using a kind of graph, or you can say Excel. Then we should have idea, because without these information we won't be getting the accurate plot of this graph. So that is why if we are targeting to calculate these parameters, that is why sometimes people assume that this Snyder synthetic unit hydrograph is bit tedious job. Okay, so in the last it is mentioned that 1/3 of the width are distributed before the peak and remaining after the peak. Okay, moving to the next. So the question here is based on Snyder method. We already have discussed synthetic unit hydrograph have three type of application. Like there are three kind of, you can say, methods. So one was based on Snyder. So Snyder gave us some certain kind of empirical equations in order to derive the synthetic unit hydrograph. Then there were certain like model based prediction. So that was Nash model or Clark's method, right? And there were one more method that we have seen, that SCS dimensionless method. Okay, so dimensionless method is also there. So here the question is related to Snyder method. So empirical equations are much more mentioned in the in his method. Okay, so here, do you know, do you have any idea related to TP and TR?
Yeah, it is from centroid to.
Yes. So if I'm plotting hydrograph, this is called as a hydrograph. Any confusion to this?
No confusion.
Because this will be a D duration and this will be a 1 centimeter of rainfall. So 1 by D, it will be a hydrograph only. So, and then if I am taking it as a
Runoff.
maximum value, okay, so tell me whether I am right or wrong. This will be a TP or not?
This is a TP.
Okay,
Capital TP, I think.
this will be a capital TP, right? Okay, so, and what about this one? This will be, okay, if I am taking it as a complete value, then this will be a TR, right?
Yeah, TR.
Okay, so this will be a TR. Now if I try to join this middle part of the hydrograph to the peak value,
And that is small TP.
then this will be a small TP, right? Now the question is related to TP and TR. So relation between TP and TR. Have anyone tried to solve problems related to these methods? Okay, if not,
No.
can anyone answer? If you people have solved this problem related to this method, then only these formulas will be in your mind. Okay, you can directly answer. But don't worry, we will be discussing one problem here related to this. So for time being, if anyone have idea related to relation between these options, can anyone answer? Okay, so it will be TP equals 5.5 TR. Okay, so more than like you can see 50% it is going, and it is multiplied by TR, not more than okay, ignore that 50%, it won't be like that. Okay, so here you can see that this was a TR value, then TPR, so that is a time from centroid to the peak. So TPR, it has also already mentioned that time difference between the centroid of an excess rainfall hydrograph and the unit hydrograph peak. Okay, and then base time you already know. I just want you all to keep in mind these parameters in your mind, because if you get confused with these parameters, then you won't be able to solve the numericals. Okay, so where we used to represent TB, where we used to represent TR, TPR, okay, where is QPR, what these mean by this, you should have some idea. Okay, so whenever we are using a TP value, then keep in mind that TP will be representing a standard unit hydrograph. Okay, so this parameter used whenever we are using a word called standard unit hydrograph. In journal we used to represent TPR. Okay, TPR in the sense what, that is a required unit hydrograph. R is representing a required unit hydrograph. Okay, I am moving ahead. Okay, we will discuss in further. Okay, now we are moving to the numerical parts. So here the question is, for a basin area of 3 km square, so area is given 3 km square. Okay, sorry, yeah, 3 km square only. Then time of concentration is also given, TC. Anyone knows what is mean by TC? Anyone knows? Anyone have idea?
The time since the start of the rainfall to reach the peak of the hydrograph.
Yes, right. Exactly. So we have idea related to TC, and then it is saying that we have synthetic hydrograph of duration 1 hour. So 1 hour it is mentioned, so definitely it will be a TR, right? Now the question here is, we have to figure out the time to peak, that means TP it is asking, we have to compute that. But I just want you all to keep in mind that this word is important, triangular synthetic hydrograph. So just before I mentioned that there are three main like major pathways through which I can achieve synthetic unit hydrograph. So first one was what? Snyder method. Then second one was dimensionless method, and third one was based on models. So here this triangular synthetic hydrograph is basically a method in this picture, dimensionless method. So here the assumption is what? Direct assumption is there that unit hydrograph will be assumed as a triangular shape initially. Firstly, we have to assume the distribution of unit hydrograph as a triangle, direct triangle. Okay, and then we have to go ahead and solve the solve this, try to bring this like a triangular distribution, and later we can apply some correction to this graph, and then we can smoothen this distribution further, and then we can get the original kind of you can say synthetic unit hydrograph. So initially they are assuming a certain kind of geometric shape, and then later they are making some certain corrections, and then they are achieving to the synthetic unit hydrograph. So here this question is bit related to dimensionless SCS dimensionless method. So do anyone have idea related to like any empirical equation which is relating TR as well as TC? Any any equation in your mind?
A is equal to N2. Balamunkar says TC is equal to 0.6 lag time.
Okay, so he is saying what TC equals 0.6
Lag time.
lag time multiplied by lag time, right? Okay,
Yes.
okay, okay. So TC for yes, for computing the time of concentration part, yes, he is right. 0.6 will be there, but we will see this equation in the next slide. Okay, so this entire method, SCS and dimensionless unit hydrograph method. So you can see the values of QP and TP may be estimated using the simplified model of a triangular unit hydrograph, right? Then for this triangle, you can see TR by 2 you can directly visible to this, and then TP is there. Okay, but if we are trying to incorporate time of concentration in this picture, okay, so this graph you can see directly. Okay, so if we are if we are using a parameter to represent the time of concentration, so time to peak will be somewhat 60% of time of the concentration. Okay, got it? So here the time of rise, that is TP, can be expressed in terms of lag time TP as well as the duration of effective rainfall TR. Okay, while we were discussing about this TP, we want to compute this TP part, right? So from this picture you can directly get that yes, we have to take this particular part TR by 2, right? So TR by 2 we got it. Then there was a parameter called TP, small TP. Okay, that is time to reach like time to the peak value. Am I right? TP. So here TP is considered in terms of TC. So if we are plotting this TP, so TP is from where we are plotting, that is the end of this hydrograph. End of the hydrograph to the point of inflection. So it is called as TC, and TC is equivalent to TP by 0.6. Okay, so using this formula that is given here, TP equals TR by 2 plus 0.6 TC, we can compute the total time of rise. Okay, now compute the value. Are you getting this value which is mentioned there? See, this is straightforward. Okay, if we don't have if we have a direct value of TR and TP, then we can directly utilize the simple geometric calculation, right? TR by 2 plus TP. But yes, for this question we don't have an idea related to TP, but instead they have what they have given, they have given the time of concentration. Now you should have some idea that TP, what is the relation between TP and TC. So yes, if you are trying to compute TP, then TP will be somewhat 60% of time of concentration. And now you have to put this value here and you have to compute the total time of rise. Got it? See whether you are getting this much of value or not. You can see the input values from here. So
0.6 of 1.25.
so TR by 2 will be what? How much? It will be 1 by 2, right? And
Yeah,
then
one.
0.6 into TC. So TC is how much? TC is 1.25. So now multiply this and add up with this 0.5. How much you are getting?
We have taken TR as 1.
No issue. So it will be 0.5, right? Let me calculate
But
also.
why? Can you explain why we have taken TR is equal to 1?
Because just you can see na 1R unit triangular
Okay.
synthetic unit hydrograph, it is mentioned in this picture. You can see na. Wait a minute. I'm just. Okay. Okay. So look at this hydrograph na. So this is representing a
Okay.
duration.
I got it. I got it.
We are taking a duration. So 1 hour duration is there. So that is the time for the storm occurring in that area.
1.25 we are getting.
Okay, 1.25. Good. What about you, ma'am? Are you getting?
Yes, 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 I got.
Okay.
Same.
Uh, Ashish, you can also tell me the answers from Balamurgan side.
Yeah, sure, sure, sure. I'll check.
Okay. Moving to the next question.
Hmm.
So here the input parameters are same. So we have idea related to area. So that is 3 kilometers square. Then TC is again given 1.25 hours. Then we have idea related to 1 hour triangular synthetic hydrograph. Okay, so TR is given here 1 hour. Now we want to compute the peak discharge, that is QP.
Q.
Now we want to compute QP value. See, if we are saying that there is a triangular kind of distribution, right? And what we have just calculated, we have just calculated a capital TP value, right?
Yes.
Am I right? And
Yes.
then we want to look up into this part QP. We want to calculate this, right? And so if you take area of this watershed, this area, 1 hour triangular synthetic hydrograph, it is given. Any kind of approach you can make from this?
So we need to use the half base into altitude formula, I think.
Okay.
0.5 into say TP half base, and this is QP is equal to, so TP we have.
Wait, Ashish, wait. Uh, for me, I'm just asking that how I can achieve meter cube from this
Area into
question.
depth. Area into depth.
But yes, that's the question. The depth is not given here. It is given only an idea related to 1 hour synthetic, 1 hour triangular synthetic hydrograph. It is not saying a unit hydrograph. No, that's a matter. That's a point. I want to just make you all see this question. So how we can approach if it is not mentioned that yes, 1 unit hydrograph it is there. It is only saying 1 hour rainfall is happening. 1 hour hydrograph we have. If we definitely, you are right, if we have an idea related to unit, like how much depth of rainfall is also occurring, then we can directly approach, we can equate the, like we can try to figure out the area, and the area will be giving what, it will be getting a volume.
volume.
So volume will be what, that will be area multiplied by depth. So here you can see that how this problem can be solved. Okay, so
Hmm.
area under the triangular unit hydrograph, that is considering as a direct. Okay, so they are actually in this question, assumption is already made, we have to take it as unit hydrograph. So depth of the rainfall will be 1 centimeter only. So you have to approach in that manner only. Try to compute that. Take depth of rainfall as 1 centimeter only.
That's okay, but we just want to know that why they have taken 2.67 TP.
2 point.
67. They half base. Base is they consider 2.67 capital TP.
Okay. So see, whatever the calculation is there, whatever you are seeing here, it is directly from their empirical calculation. Okay, so just for your information, whatever the constant you are looking at na, they all are empirically derived.
Okay, 2.67 TP. Okay,
Yes,
okay, okay.
you have to
Got it.
take this value.
Hmm. Got it. So half into 2.67. So TP is our
and and
2.5.
and from this graph also you can have some idea, right? Because if you are taking another part of this, you will be like, if you are assuming this triangle as symmetric, let's assume this triangle as symmetric, then you will be having how much TP will be again here only. So if you add up this, so how much you will be getting, approximately 2 TP, right? Am I right, Ashish?
Yeah, yeah, correct.
2 TP, but I just want you to keep, like think in that manner also, that not always this triangle will be symmetric. There could be a possibility that triangle is going like this, there may be a possibility that triangle is going like this, then how you can counter this? So in order to compute this, they they may have tried to balance the unsymmetry by using this particular much of value, that is 0.67, you can say 2 plus 0.67, you can assume it like that. So unsymmetry have been encountered by considering a value of 0.67. But if you take a symmetrical part, then there will be a condition that yes, it will be 2 TP. Got it?
Hmm.
Yes.
TR we have.
Don't confuse with this 2.03. You can directly use 2.08. Okay, not a issue. It won't make too much change in the values. This calculation you may have got it easily, right? This is
Yes,
simple one, because it is just a volume equals area into depth. So
only we
after
get confused in this capital TP and small TP.
so now you are getting or not?
Yeah, yeah.
Okay,
I'm
cool.
trying. We have to do 2.08. It's yes, 2.08.
How much you are getting?
So I'll get 2.08 into area. Yeah, how much area do I have? 3 divided by 125 into 3 divided by 1.2. 4.992.
Okay, good. Ma'am, what about you? I hope Balamurgan, you
Yeah,
already
he,
also got
yeah, he
the.
answered. He answered
Yes, I got
4.9.
it.
Okay, okay,
4.91.
yeah. So, Ashish, I hope you already got what this empirical relation means. Okay,
Yeah,
every
we have
time
to write
whatever
it.
the empirical relation are derived, you should have some logical thinking from your side also. It won't go beyond that, na, right?
So small TP is equal to 2.67 capital TP.
Capital TP. But
And then
from
next
your,
is the
yes,
capital TP is equal to TR by 2 plus TP.
yes, this is simple now. This is
Yes,
only,
we'll,
you can
we'll
see
learn
this
it.
is geometrical relation.
Hmm.
TP is just a TR by 2 plus TP. That is the summation of this. So you
Okay.
already got this simple equation. But the fact was like we have to keep in mind that how we can achieve the base time. So that was a TB. So TB will be
TB.
definitely TP of like multiplied by 2. Like if you take a other part of triangle, then it will be coming approximately 2 TP, right? But now,
Okay, okay.
in order to account the unsymmetry of the triangle which may
Hmm.
have occurred, so that 0.67 something factored have been taken into account. Okay, should I move
Okay.
ahead?
Okay, okay, okay.
Still anyone to discuss? Anything to discuss? Ashish, any query?
Just give me 1 minute. I'll make this figure so that um,
Ha ha ha. Yes, yes, yes. I'm just wait a
so
minute.
for upcoming question we can just consider it.
Yes, yes, yes. Of course. Why not? I'm just erasing this. It will be good for you.
So this is small TP. This is or this is TP. This is TP. Okay, now we can move.
Okay. Okay. The question. This question will again have the same information, but the
Hmm.
here whatever Ashish was just asking, the question is related to TB. That is time base. We have to compute this value, right? So can you calculate now?
Hmm.
TB
So
will be
that
what? TB will be, you already got the relation, na? That is,
yes, TP is equal to TR by 2 plus TP. That is
yes.
capital TP.
I'm just asking about TB. TB will be 2.67 multiplied
T,
by how much?
TP.
Okay, right. So it will be TP, not TP. It will be
Capital TP.
capital TP, right? So now compute that. So you already have the value of TP. Multiply it with 2.67. You will be getting a direct value of time base. That
Yeah,
is
yeah.
TB.
So we have capital TP. Is the time. We have TC. We need to calculate TP also. Capital TP.
Yes, capital TP firstly you have to calculate, then you have to multiply it with 2.67.
Hmm. So we have to do TR by 2. No, no, no. This is not TR. Okay. Plus small TP.
In
So
the earlier
TR
question,
is
you already have the value of TP,
3.25
na?
by 2.
How
Yes.
much TP you have calculated? It will be
1.25.
1.25. So multiply it with 2.67.
1.25 into 2.67. 3.33.
3.33. Okay, let's wait for others.
Yes,
3.33 hours. You are getting.
3.3,
Okay,
3.33.
ma'am, you already also got the answer. Balamurgan replied or not? Ashish?
Wait a minute. Yeah, he replied 3.33.
Okay, that's good. So answer is 3.337 hours. Okay. So if you got the answer, I'm moving ahead. Okay, now this question is, this will take a lot of time as well and lot of computation. So I want you to keep with me. Like this question parameters, like whatever the information you are getting now, it will be repeated for like 2 or 3 questions. The only thing will be what it will be varying the questions, like what we want to what question is asking. So you have to, whatever the things you are making, keep it with you in proper way.
Mhm.
Okay, so this question is related to a synthetic unit hydrograph. Okay, and Snyder method is being used. So Snyder method you can see. So for Snyder method, just for your information, I want to add few things, that this method can give an information about the unit hydrograph even if we don't have any gauging site. No gauging site is there. Like this catchment is not gauged. I don't have any information related to unit hydrograph. Hydrograph in the sense what? Discharge versus time. This relation I don't have. But I have another catchment and I know the information like hydrograph. I have information related to a hydrograph. Then I also have information related to water set characteristics. Also, I have idea of geomorphology of this basin. Water set characteristic will account everything. Geomorphology, then site, shape, everything. It will account. Now these water set characteristics, there is a one condition, that if we want to derive a unit hydrograph for an ungauged catchment, we should have any water set with similar water set characteristic. Similarity will be in what sense? Water set characteristics should be same. If we can find any kind of catchment which is having a same water set characteristics.
Hello? Sorry. Sorry.
Okay. So we can easily derive this unit hydrograph. So for that, this question have provided two water set. One is water set A and then another one is water set B. So water set A, what information we have? So we have 2R unit hydrograph. So hydrograph information we got it. How we got it? That is a rainfall and runoff relation. By utilizing these information, we have already derived the 2R unit hydrograph. So these things are known for water set A. Now some water set characteristics are also given. That is a basin lag. Okay. Then peak discharge is given. Area of the catchment is given. Then length of that catchment is given from the outlet to the extreme point. Then there is LC. One more point. Like this is the length of the catchment. Like not the catchment from the outlet. If you are having an outlet and you are also having the centroid of this catchment, you have an information like yes, this at this location centroid of this entire catchment lies. So taking the distance between the output to the centroid, this LC have been taken. So you also have this. These all information can be taken easily from topographical maps. Keep in mind, these entire information can be taken from topographical maps. You can directly get these values. You can have idea about the area. Okay, nowadays people used to prefer plotting everything in GIS. Okay, geographical information interface. So from there they used to get these data, that area, what is the length of the catchment, then what is the value of LC. Okay, so you have this information. Now watershed B, this watershed is, you can say, a required unit hydrograph. We need to compute a unit hydrograph, so I am just saying that required unit hydrograph, keeping in mind that similarity is given. So now what are the inputs they have given? So area is given, area of this characteristic this watershed is given, that is 1200. Then length is given, length of this watershed is given 120 kilometers. Then LC is also given 100 kilometers. Now the question is asking that we have to derive 4-hour synthetic unit hydrograph for watershed B using the Snyder method. At first we have to derive this. Then they are asking that we have to compute peak of that unit hydrograph. So the question is all related to QP. QP of what? 4-hour synthetic unit hydrograph. This is the question. Now the big question come up here is what? That how we can approach this problem. So before going to this, I just want to mention few information. Right? There should be, like, when what we have to do is avoid everything. Keep one line in your mind that we have to compute some coefficients we have to compute from watershed A. Okay, and we will utilize those coefficients in watershed B in order to derive then unknown parameters. Unknown parameters will be, like, it can be a peak discharge, it could be a time base, okay, it could be a time to reach the peak value, okay, any parameter it could be. But one crucial information that you have to see is that we need to generate coefficients from watershed A, okay, and those coefficients will be used in watershed B in order to derive other parameters. Okay, so just I have summarized these data in this slide. So time of excess rainfall hydrograph, so it is given 2 hours. You can see that for watershed A, how much was what will be the TR value? TR will be a 2 hour, right? And depth of the rainfall will be how much? It will be a 1 centimeter.
1 centimeter.
Right. Okay. Now note down the values. Basin lag is also given. Basin lag is nothing. It is a peak to reach the this is a time to reach the peak value. Okay. So basin lag is given. So it is 24 hours. Then peak discharge is also given. 50 meter cube per second. Area is given. Length is given, and LC value is also given. Now this is for watershed B. Okay. This is for watershed B. Required duration of excess rainfall hydrograph is 4 hours. Area is given 1200. L length is given 120, and then LC is given 100 kilometers. Now I just mentioned you there will be a 2 major coefficients. One coefficient will be CT, and one coefficient will be representing a peak value. One parameter will be related to a time, you can say, okay, and then another one will be representing a discharge kind of thing. And these 2 coefficients will be utilized in case of this watershed B, and we can directly get the unknown parameters. Got it? So before going to this question, there will be a one check process is there. We need to check the given data, not entire data, only the unit hydrograph. Whatever the unit hydrograph we have been given, we have already provided a 2-hour unit hydrograph, right? But we need to check like there is an before applying this method, we have to we have to firstly check that yes, whatever the unit hydrograph we are focusing on, it is standardized or not. Okay, so standardization in the sense what, that yes, we whatever the value we are looking for, say if I'm saying that TR, okay, so TR here I am taking as 2R, but sometimes what happens, while we are going ahead and solving a problem, there may be a chance that this TR value won't be coming in a integer, it would be coming like 2.67 or something if we are going ahead in calculation. This is for what? This is for the Snyder method I am talking about. Snyder method. So in order to avoid this kind of disparity, you can say, we have to firstly check whether this unit hydrograph is standardized or not. So for checking the standardization, we have to follow this T of PR. Okay, like we have to follow this relation firstly. If this is not equivalent, then that means that it is not standardized. If it is not standardized, then definitely it will be making impact in calculation of TP. That is the thing I am just making you to look into this. TP will be changed. You can see we already got the value of TP, right? In the question itself, we have that after 24 hours we can have a peak. Okay, but if it is standardized or not standardized, because in case of standardization, if I am saying that yes, this unit hydrograph is standardized, so that means whatever the TR value is given, and we are looking using this empirical relation, and we are computing the TP value, we will be getting somewhat 24 hours only. Because
Okay, same TP will get
yes,
it.
right. But now if it is not standardized, then TP value will be somewhat different using this TR only. Using TR
Okay.
value, if I am calculating a TP value, then it is not coming same as 24 hours. So that is why I am this method is firstly checking the standardization of this unit hydrograph, given unit hydrograph. So the condition what should it fulfill is that this relation should be fulfilled. Okay, now these parameters have simple meaning. TR is nothing, it is just a
One.
value of whatever the TR value, small TR value we are seeing, that is a 1 hour duration or 2 hour duration of unit hydrograph. Okay, so this is representing a duration of the rainfall. Okay, and then 5.5 is just a factor which have been multiplied in order to achieve
TNPR.
time to peak. Yes, now if it is not equivalent, that means it is not standardized. Now check, I have just kept this numerical part. So 5.5 multiplied by TR will be how much? For
11.
watershed A it is 2 hours. So if I am multiplying it with 5.5, I am getting a somewhat 16 hours, which is not equivalent to 24 hours. That is the thing I want you to see. This is not equivalent to 24 hours. In general, if it was standardized, it may have equivalent, it may have been equal values, but now it is not. So yes, it is not standardized. So that means we need to recompute this TP value. Okay, so how we can compute this TP value? So basin lag we have to compute it for watershed A. So TP will be computed based on this empirical relation, 22 upon 21. T of NPR, we already got the T of NPR value, right? T of NPR will be how much? It is given for the watershed. This watershed have already been given a value. It was initially what
24
was
hours.
yes, it is actually representing an initial value that is given for this hydrograph. Now we are computing a modified value, right? Keep in mind that we are now computing a somewhat modified value. Modified value because it is not standardized. So TP we are computing. If we have a standard value directly, then we don't need this step. Keep in mind. Now we have value of TNPR, that is a 24 hours. Okay, and then what about the TNR value? TNR is nothing, it is just a 2 hour value, that is the duration of the rainfall. Ma'am, are you getting what I am just trying to explain?
Yes, yes. I'm
Okay,
following.
okay,
This
good.
22, why this 22 by 21?
Ma'am, this is this is not from my
Empirical,
side, this is a direct empirical relation. So
empirical. Okay.
yes, so it is just a factor which have been taken into account. Okay,
Okay, okay. Thank you.
yes. So now if we substitute the values here, 22 upon 21, and we are providing the value of basin lag which was given earlier for this watershed A, so I have provided 24 hours. Then TNR will be how much? It will be a duration of the rainfall, it will be a 2, and it will be divided by 4. And now you can compute from your side, you can compute and you can look into the value of time base, basin lag. Okay, yeah, base time, not base time, I can't say a base time because it is an entire width. Okay, but if we are talking about the TP, then definitely it is a time to reach the peak. Up to the peak value it is representing a time. So now you can see that this value is getting somewhat more than 24 hours. Okay, so this is the modified basin lag for watershed A. Are you getting this value? Let me
Yes,
calculate also. Okay, are you
yes.
getting this? Okay, if you are getting, then Ashish, are you getting this value?
Yes, yes, I got it. 24.619.
Okay, good. In parallel, you can also tell me the like what are the replies from Balamurian side also. Okay. Okay. So now once we got the value of like modified value of TP, now our target is the same. What just I mentioned before approaching the question. What we need to compute is that two major coefficients. So two major coefficients is what? That is a CT, which is representing a kind of time factor, and there is one more parameter that is representing CP, coefficient related to a discharge kind of thing, right? These two parameters will be transferred to the watershed B. Now from this picture you can see how we are approaching to compute CT and CP. So the first step was what? That was a standardization. So we already did, we have already checked it and we have computed, we have modified the value regarding this. And now see how we can compute the parameters, that is the coefficients. How we can compute this? So if we want to compute a coefficient related to a time, then you have to take account what parameters? TP. Firstly you have to take a parameter TP, then you have to give a value of L, and then you have to also give a value of LC. These three parameters if you give, then you can directly compute the value of CT. Okay, so now compute this value and tell me whether you are getting this or not. You already have you got the TP value? Do you have TP value?
TP is 24.619.
Yes, 24.619. Yes, I am just checking your presence of mind also. Okay, so that's good. TP is 24.619. Now tell me the value of L. L is how
L
much?
is 30 kilometer.
How much?
30.
30 kilometers. Okay, good. Then what about LC?
LC is 15.
15. Good. Oh, 15 kilometer. Good. Now put in these values in this formula and tell me the value CT. If you will be having a calci kind of thing, or maybe an advanced calculator in your phone, you can directly compute this. The only thing is that you need a this 30, like
Yeah,
calculation
we'll
of
do it.
which is raised to a power. Okay, that is important. If you are getting that accurate
Yes.
value, then you can directly compute. Let me calculate parallelly. I am also calculating 24.609.
Some mistake I did.
It may be possible that values may be somewhat different.
Yeah, I'm getting
5.25. 5.25.
Okay, 5 point something you are getting. How much? 5 point
25.
5.25. Okay. I am taking a TT value here.
6.25.
And what about the CP? How much you are getting CP?
Yeah, I'm getting 5.25.
Okay, 5.25 you are getting. Okay. Wait a minute. Wait a minute.
20, 15. 3. 6.25. 4.75. Yeah. CP.
Okay, so if for this question, I guess 5.25 is a correct value. This value may get lower if we are if we are increasing this multiplication value, right? If we have more L and LC value, then definitely this parameter will get reduced. Okay.
Hmm.
Yes. So
CP is correct. It's 6.6325. I got it.
325.
yes.
That's okay.
Okay, so CP is correct. Make sure CT will value will be from your side 5.25. Okay, don't go with this, because in further slide there may be possibility that CP value may be taken as 2.41. Okay,
Mhm.
this is an error. Okay, so now we got the coefficients now. Okay, now we have to transfer these coefficients in water set B. Okay, and see how we can compute the unknown parameters now. So now we are at water set B, and where we need to compute the required unit hydrograph, right? Now the first thing here is related to basin lag. How we can compute the basin lag for required unit hydrograph? So this formula is not new. Okay, this formula is just this one. Only thing is that this 24.619, it have been replaced by TP capital R, right? From this you can see CT, TP upon something, this one. So just this denominator part is getting multiplied, okay, by CT, and we are getting a TP value. Don't confuse with this. So TP are using this empirical relation, compute the value and tell me how much basin lag you are getting.
TPR is equal to 0.75 LCT ULC. So we have to put the CT value is 5.25.
Yes. Let me compute.
5.25 L is okay. We used to do 120 and 100. Okay.
It may be coming around 60 or 60, 65 something.
65.91 I'm getting.
Yes, yes, yes. So
65.914.
Okay, Ashish, keep telling me the answer from Balamurgan also.
Oh, yeah.
What is his reply?
Sure. Yeah, he replied 65.914.
Ah, that's good. Good. So now we are at then ungauged catchment. So in order to compute the TPR value, that is the basin lag, so we have used this formula. Now whatever the you can see in this fashion, we have firstly approached like this. This is an pathway, this is an step that we did, and we finally come up with CP and CT. Now we are going back. Can you feel this? Using these parameters we are going back again. So firstly we were having TR, then we come up with TP, then we again come up with TP dash, or you can say modified TP, and then using the certain relations we come up with computing the CT and CP. Now again we are going back. How we are going? We are computing first TP dash, or maybe you can say TP, and then we are again converting it in terms of TR, and then definitely if things are not matching, like again we have to check for the standardization, right? So if standardization is not matching, because I just told you, if whatever the unit hydrograph we are getting, that is not standard, then definitely this TR and TP, whatever the values we are getting, it may not be matching, right, accurately what we are looking for. So we have to revise it, we have to modify it again. So now from this picture I am just summarizing it, that how we are approaching this problem. Now compute this TR, this TR value, that is the duration of this unit hydrograph, how much you are getting.
$11.984.
Okay, so you are getting somewhat 11 point, how much?
984.
984 hours you are getting. No issue. Good. So it could be approximated as 12 hours also. Now see, we got the TR value as 12 hours, but our what was our target? What we have been provided in the earlier question, it was asked in the question. You can see for this watershed B, we need a unit hydrograph for a duration of 4 hours, right? So 12 hours we are getting, but still we need 4 hours. Now there should be some modification. Now we have to make it in order to get this 4-hour unit hydrograph, and that modification should be done in base time. So again, at the earlier case also we have made a change, modification in TP value. Now we are again making a change in TP value. So how we are making this change? Using this empirical relation. TPR, so TPR value we already got 65.91,
Hmm.
and then you have to keep put this value, that is TR in the sense that you are getting 12, then TR dash that you are getting 4, and it should be divided by 5.5. Then tell me what is the value you are getting. That is a modified value depending on the
1.45.
duration of storm.
1.45.
Okay, you are getting 1.45. Okay, wait for others, let me calculate also. But you are getting 65.91, subtract
Yeah, this is. I did some mistake.
12 minus
No, 65.91.
Ashish.
64.45.
Yes, I'm also
Yeah.
getting a larger value, 64 point something. Ashish.
1 minute. I did some mistake.
Yes, 64 point somewhat 45 value.
64.45.
Yes, I just want you all to kindly focus on steps. It should not be confused with you. It should not create some confusion. Okay.
Hmm.
So now we finally got the modified basin lag, that is TP dash. Now we have computed this basin lag. So we already got the final value, that is a TP dash. This is a final value. Okay, this is the final value of this watershed. Now we need to compute the time to peak, right? Time to peak. So time to peak, remember that equation, TR by 2 plus TP. And can you remember that? This is the same relation.
Hmm.
See, I'm
Yeah.
just summarizing it in reverse way. Okay,
Yes,
why
yes,
Okay.
yes.
we have preferred this much of long calculation? Why? Because we need to compute peak discharge. So peak discharge can only be computed if we have this value QP. And this QP, how we can compute this? We can compute this by taking 2.78 multiplied by CP factor, that is a coefficient. This coefficient is important, so that's why we have followed this much of long step. Okay, so are you getting this? Like how much value you are getting? It will be definitely, it may have been changed. So 64 point,
66.45.
okay, how much? 66.45.
66.45.
It will be in hours. Good. Now compute this peak discharge value, and this keep in mind, this QP will be, whenever we are representing a small q, it is just per unit area. Okay, so QP is, we are computing it as per unit area. So use this relation, 2.78 CP upon TPR. Okay, here how much it is saying. Okay, so here this relation is considering TPR, not TP dash. Okay, so it will be 65.91 something. Wait a minute. This QPR, okay, QP, it will be multiplied by TP and this. Okay, okay, yes. So it is using TPR, not a modified value. It is using a original value. So
Point
time
not
to,
two
yes.
six.
How much?
Point not 267.
0.0267.
Two. Yeah.
This much. Okay, sorry,
Sorry,
0.02.
no,
Yes.
0.0267.
Okay, okay, no issue. And unit will be meter cube per second, kilometer square. See, uh, just for your information only, this 0.0267 we got it by considering lower values of L as well as LC. if if we could have more value, like larger value of L and LC, we could have achieved this much or maybe more than that value. So that is the thing that I just want to make you to, like, it is just a logical observation. Now if we want to compute peak discharge, that is overall discharge, so it will be multiplied by area, right? So how much you are getting?
Thirty-two.
32.04, right?
4. Yeah.
Yes, 32.04. It will be in meter cube per second. Now summarize this question. Can anyone summarize what we did? What we were given? We were given an information related to a watershed A.
Mm.
We try to compute the coefficients using the, like, duration of the rainfall or basin lag, and then again we followed a reverse process and computed the unknown parameters in the sense I am just talking about a peak discharge. So peak discharge can be computed only by using a coefficient called Cp, but that Cp is not alone taken into consideration. Instead we also need to compute the basin lag for that watershed where we are computing the unit hydrograph, because if you look into that watershed, we don't have any information, right? So we have to compute every parameters, then only we can finally achieve that yes, this is the peak discharge. Now see the next question. So this question is asking about the time of that, all over the parameters will be same, okay, and the only thing it will be changing here is time of rising or time to peak. So can you tell me the parameter which it is asking? So it will be a TP, am I right? Do you think it will be a capital TP? Any idea? Because all the parameters are same.
Time of rising or time of peak is
Time to peak, it is saying that time to peak. So time to peak is in the sense what, like I'm plotting a unit hydrograph like this, and this is a peak, so this will be a capital TP now.
66.45.
How much?
1 minute.
Okay, let's see. So see, whatever the calculation you are going to see, they will be uh, as per whatever you have calculated, because there, it has already been, like, there was some error in this earlier problem. Definitely it will be followed in the next question also, but yes, whatever the calculation you have made, that are true. So see, again we have preferred to check whether this unit hydrograph is standardized or not. If it is what not standardized, we have tried to compute a modified basin lag, okay, and then we have tried to compute the coefficient. So CT and CP we have again computed. This CP, keep in mind, this CP is important in order to compute the QP, discharge, okay. So this is important. And then CT, if we are looking for any kind of information related to a time, okay, time of that unit hydrograph, where we are required to find out a unit hydrograph. So this CT parameter will be important role, it will make a key role in that, because using this only you can compute TR, you can compute TP, but when you utilize this coefficient, then you can easily derive the QP value. Okay, don't confuse. Now see, again the things are same. Now we are here to the required watershed B, where we need to find out the unit hydrograph. So we have again consider this empirical relation, and then we have come up and tried to figure out what is the TR, that is duration of the, what could be the
Unit hydrograph.
duration of unit hydrograph. And then we
Mhm.
see that there is a change, a slight change in this. Then again, since this TR is not matching to whatever we are trying to like we are trying to compute, we are trying to compute, so it is not matching, so we have again tried to modify it. Now again, when we have this computed all these things, then we reach to compute time to peak. So time to peak will be how much? It will be a modified value that was we were getting, and then it will be multiplied by
66.45.
yes, it will be. Yes, there is some error in this 66.45. Ashish, how much you are getting?
66.45.
That's good. Yes, so it will be same. Can you tell me the answers from Balamurgan also? Is he getting the answers or not?
Yeah, he said 66.45.
That's good. Okay, now moving to the next question. Again, the whatever the information you already have and you already calculated, these all information will be the same. What they required to ask, what they are asking is that TB. Now they are asking about TB. So I am sure that you are knowing that empirical relation. Okay, that relation between TB and TP.
Yes.
Any idea related to this?
2
TB
into
and TP.
TP.
Not 2, not 2 to P, 2 TP. It will be somewhat 2.67, I guess.
67.
Oh, okay, okay, right,
Yes.
2.6.
So the same procedure is followed. We are looking into the final aspect. So yes. Now, okay. Wait a minute. That was for dimensionless. Okay. Keep in mind, we already have jumped to the next method. This is a Snyder method, right? Snyder method we are, but that whatever the relation you are saying, this is true, but that was an applicable for SCS dimensionless method, right? Where uh, assumption is made that unit hydrograph will have a triangular kind of distribution, right? So that was for whatever the empirical relation was there. So that is applicable for SCS and dimensionless method. But when we are dealing with the Snyder, then definitely empirical relation is somewhat different. So we have to utilize this empirical relation. So TB in terms of QPR, it is dependent on QPR. Now we have idea related to peak discharge occurring in the watershed. Based on that, we have to compute the time of base. Got the idea? How much value you will be getting now? QPR you will be having idea. So it was of about 0.02. Am I right? If I'm correct.
Yeah, correct.
Okay, so you mentioned this. So compute this value by putting this 5.56. It will be divided by 0.0267. And don't forget to convert this value in hours, okay? Because whatever the value you are going to put, it will be having a unit of seconds. Okay, I'm just mentioning here the units also. Okay,
So I'm getting 208 hours.
208 hours. Okay, it may be correct. Let others also calculate.
208.239.
What?
208.239.
Okay, no issue. If I'm trying to convert this second into hours, if I do this, then how can I do this? 60 into 60, it will be divided by like this, and then again.
Divided by 60 into
Okay.
60.
Wait a minute. This QP is there, na? Okay, so there is somewhat confusion in the units, don't you think?
Unit is in meter cube second per
Is these units are correct, do you think?
second. 5.56 is into
If we are taking a unit of if I'm putting here a unit of meter cube per second kilometer square, right? Then we want what? We want a unit of hours, right? But here the question here is that in the numerator part I am getting a kilometer square, but in the denominator part I am getting meter cube. So though if I am opening this, if I am converting this, I will be getting a meter in this denominator, don't you think?
Balamurgan says do not convert because it is empirical.
Okay, okay, okay. Yes, it's possible, right? Of course, yes.
Yeah, he is right.
Yes,
He
so
may be, yeah.
QPR it will be directly having a value of in units of this only. So we directly have to substitute this in unit of meter cube per second kilometer square, and then at the in the result we are getting somewhat in matlab,
208.24.
yes, that is correct. It will be directly in hours only. Yes. Okay, I hope you got these things clear in your mind. Is it clear to all? So Bala Murugan here, you are right that yes, we don't need to change the units here. Sorry, wait a minute. We don't need to change the units. Okay. So now related to this question only, there is one more problem left. But I guess if we are looking into that, because that question also account some graphical representation. But if I consider this, then it will definitely take 15 or 20 more minutes. Yes, before that, there is one more question. Okay, yeah. There is one more question. It is related to computation of peak runoff in the catchment. We can compute this within maybe 5 minutes only. Okay, don't worry. Okay, so question here is, we are provided with the 2-hour unit hydrograph. So duration of the storm is 2 hours, so T is 2 hours. Then effective rainfall is how much? ER is 1 centimeter here, it is given. 2-hour unit hydrograph, what are the ordinates they have noted in the at the outlet. So these are varying with the time as well as the ordinates. Ordinates are in the unit of meter cube per second, so definitely this is representing a discharge. Now from this table itself, you can have some idea that yes, once readings are getting increased and there is peak of 120 meter cube per second at a time of 8 hour, and then again readings are now getting decreasing again. So peak you can imagine like this is the graph. So peak where we are getting, it is of about 120 meter cube per second at an hour, at a time of you can say 1 hour. Okay, so this is a general interpretation of from this table. Now see, the question is saying that this same catchment is experiencing different storms. Okay, different storm in the sense what? At 2R you are having an accumulated rainfall of, you can say, 4 centimeter. At 4R we have accumulated rainfall of 6 centimeter, and at 6R I am getting an accumulated rainfall of 10 centimeter.
10.
So here storms are getting like it is different for every case. You can consider this as one storm, you can consider this as second storm, and you can consider this as third storm. And then what they are asking the peak runoff in the catchment, like for taking an effect of all these 3 rainfall events, we have to derive a unit hydrograph, right? And one more thing they have given is that phi index, that means how much water is infiltrated, rate of infiltration is given 0.2 centimeter per hour, and also they have given base flow have also been given. And then they are asking about the peak runoff will be what? It will be a storm hydrograph, like whatever the direct runoff value we will be getting, we will be adding to base flow, and then total value will be called as total storm runoff hydrograph. Got it? Okay. Now I just want you to keep one thing in your mind, that whenever we are dealing with storm, like small storm events, and they are getting lagged by some time, and we want to compute the overall effect of these small unit hydrographs. Okay, so you can consider it as 0 to 2, there would be some peak which have been come up, then there could be some another hydrograph between 2 to 4 hours, and then other 4 to 6 hours. So now what question is asking is that we need to figure it out, firstly we need to figure it out the overall effect of this small unit hydrograph, and then we have to determine the peak of that hydrograph, QP. So we need QP of this bigger hydrograph. Okay, so the approach will be what we are looking into this. Okay, so can you tell me how we can determine the effective rainfall ER value? For this for time being, what we have been given accumulated rainfall, right? So accumulated rainfall is given. It is not an effective rainfall. Effective rainfall will always be a kind of surface runoff, you can say. Okay, runoff depth we are saying. So ER will be generated after subtracting the phi index, like infiltration, how much infiltrated firstly we have to determine, and then we have to subtract the incremental rainfall with that, and then only we will be getting the effective rainfall. So we have to compute the ER for every storm, like for this 2 to 4 which is given, then again 4 to 6, then again 6 to 10, we have to compute this. Now tell me what would be the ER value for all the cases, then only we can approach. Now we can follow that process. So tell me, wait a minute. Yes,
We need to calculate the incremental depth.
yes. So
in the incremental
depth.
time interval.
So incremental depth, how much?
So first one
2,
is 0.
4, 6 hours it is given, time is given. Now we want to compute the incremental. So incremental will be what? That is a difference between two intervals. Two storms. So
right.
In first case, I am just writing. I am leaving it as empty. Now for the second case, how much you will be getting? You will be getting 4. Then other will be 2, and another will be again 4. Am I right?
Yeah.
Okay, now you got the incremental value in terms of centimeter rainfall increment. You got it. Now I'm just asking about the loss. Tell me the loss. So loss will be how much? It will be 0.2 centimeter per hour. It is given, right? But you can see every storm is occurring for 2 hours, right? Difference you can see na from time to time. It is occurring for 2 hours. So
Then we need to
if I multiply
multiply.
it with 2, then I will be getting 0.4 centimeter in total. That is a loss.
Loss.
So 0.4 I have got it in terms of loss. Now what will be the effective rainfall? ER. ER will be
Loss
the
into the time.
what?
Yeah, you need to minus 4 minus
Rainfall
0.6.
minus point.
Yes. So 4 minus
3.6.
0.4, it will be 3.6. Then 2 minus 0.4, it will be somewhat 1.6. And
1.6.
then 4 minus 0.4, it will be somewhat 3.6.
We need
When
to
I
add this one.
No, we don't need, because we only need an idea of effective rainfall, how much it is occurring.
Okay.
Okay, and then accordingly we will multiply it with ordinates. Ordinates are what? These are the ordinates.
Okay.
Recall some of the questions we already solved where we were dividing the ordinates with effective rainfall. Okay, this is the problem. Now see, we have inputs like phi index, we have inputs of base flow, and we need to compute the peak runoff in the catchment. Now what we did, we already computed this part, right? You already got the idea about this table. Now move to the next table. So here what are the information that you have? So we have time. This is the table that you are looking at now. Okay, so first column is this, second column is this, second column is nothing, it is just a recorded data of 2-hour unit hydrograph. So from this you can have idea that this 2-hour unit hydrograph, that means 1 centimeter of effective rainfall is occurring. Whatever the data have been given, it is only for effective rainfall of what? Only 1 centimeter, right? But look at the question.
We
Sorry.
have three different storms and three
Yes.
different effective.
Actually, this is given for the reference purpose, right? This is for our reference. That yes, for 1 centimeter of effective rainfall, we are getting this much of data. But yes, if you see the data carefully, so for first storm, this is the first storm, 2 hours. So entirely within overall in 2 hours, we are getting an effective rainfall of 3.6. It is not 1 centimeter. 1 centimeter have been given for our reference purpose, but 3.6 is a total total effective rainfall occurring within over a 2 hours of period. So what we have to do, if we want to compute the DRH, like that is a direct runoff hydrograph. Why DRH I am adding? Because it is not added up to base flow. When I will add DRH with base flow, it will be coming as a total storm hydrograph or total runoff hydrograph, you can say. Okay, so Ashish, tell me, if I have 2-hour 1 centimeter hydrograph and I want 2-hour 3.6 centimeter effective rainfall hydrograph, what I will
So
do?
we multiply it 3.6 by 25 to get
Right,
9.
yes.
Yeah.
And now multiply it with and check the results, what you are getting.
Yeah, first one is 90 is correct. 144 I got it. 324 is
Okay,
9.6.
now you got this idea about this table, this column. Okay,
Hmm.
now shift to the next storm. So next storm is how much?
1.6.
Yes, but now see the things. Whatever the scenario it is generating after 2 hours. Like after one storm finished,
Hmm.
then the things are arising for storm second, right?
Hmm.
Are you getting the things?
Yes.
So
So
for
point
this
8 I think.
purpose, what we are doing, just from the graph you can see, this was a small hydrograph, 0 to 2, right? And then again, this hydrograph is plotted for we need data for 2 to 4 hours,
Oh. Yeah.
and then we need data again for 4 to 6 hours. But are you able to see that whatever the data it has been given, it is not individually for 2 to 4 hours. It is for entire, like whatever the
Cumulative.
value we are getting. Okay, 1 centimeter it is sure, it is not an issue. Okay, you can imagine like in this fashion that yes, we are having the data, like entire data, this entire plot. Okay, this is the data, this is the your entire data what have been given in the second column. But keep in mind that this entire data is plotted for 1 centimeter of excess rainfall only. So we don't have idea about 2 to 4 hours that what is happening. So what we did, what we will do, we will shift this entire plot by 2 hours. Initially we will shift this because whatever the information we are trying to extract, this is between 2 to 4 hours. So we are lagging, we are just shifting this hydrograph by 2 hours. Then we can see that what is the scenario, because now we will look, the entire hydrograph will be shifting like this. It will be shifting from 2 to, again time we can't predict, because time it will be going beyond that also. So now this entire hydrograph have been shifted by 2 hours. Now if it gets shifted, then what will be the values you will be getting? So you will be getting 0, then 25, then 40, then 90, then 120, then 80, 65 and so on. Now this is again a 2 hour unit hydrograph for this storm. Got it? Only 2 hours, because event is happening for 2 hours only. Now you have to multiply this.
Just a minute. How you got 0, 25, 40?
I'm just lagging it. I'm lagging in the sense what? I'm just taking.
Okay. I got it.
Okay.
Okay,
And then
we got it.
keep in mind that whatever this data you are getting, this is a 2 hour unit hydrograph again. But this have been shifted. This have been lagged by 2 hours. Okay.
1.6
now just I mentioned that this is a unit hydrograph, but how much rainfall you are getting in this storm? You are getting 1.6 centimeter. So in order to get the overall effect of 1.6 centimeters rainfall, you have to multiply it with these values. These whatever the values I have just wrote.
Lagged values.
Yes, lagged values, right. And the similar scenario have been taken for 6 hours also.
Okay.
Ma'am, are you getting what I just mentioned?
Yes.
Okay.
So you have to consider the same 2 hour unit hydrograph for the second storm of
Yes, right.
affected.
Right. So Ashish, now you can see for every storm, peak values may be different. It won't be same for all, right? And also, whatever the peak values we are getting, it may have occurred in different time interval also. Like for 2 hour storm, I'm talking about this third column. So a storm maximum maximum peak runoff peak I'm getting here is 432, and which is found at an 8 hours, right? But for 4 hour of unit hydrograph, after 4 hour, you are getting a maximum peak of about 192. So peak has been what? It have been increased or decreased?
Decreased.
Yes, it have been decreased. Now, because why it was decreased? Because the effective rainfall was 1.6 only. But after coming to the 6 hours, again we can see that yes, I am getting a peak value of 432. But at how much time? For 12 hours. Now at the end, what you have to do in the last column, what you are looking at, just add up these 3 columns, 1, 2 and 3, and don't forget to add 15. 15 was our base flow. If you want to figure it out, the total storm hydrograph, then you have to add base flow. It is mandatory. Ashish, any confusion in this? Are you getting the values?
Yes, no confusion.
Okay. Okay, tell me whether you are at least try to compute the value up to this point, so that you should have some
288
idea that yes, you are getting.
plus 192 plus 324. It's 804.
It's 804 you are getting.
10th number.
Okay,
The peak
10th you are
discharge.
getting. Okay, let me add also 288. Have you forgot to add 15? 15,
Yes.
because you have to add that waste flow also, na?
Okay. Yeah. Correct.
Don't forget that the total flow will be a summation of DRH plus base flow.
Base flow.
Yes. See, sometimes
Yes, we get 819.
819. Okay, that's good, ma'am. Sometimes while you are solving the problem, you may get confused with DRH. Maybe you may be having a word like UH. Okay, then there may be a word like total storm hydrograph also. Storm hydrograph sometime it is mentioned, or total runoff hydrograph sometime they mention TRH. So if TRH is given, then you should have direct idea in your mind that yes, base flow has already been accounted in this. So in order to proceed for generating a unit hydrograph, you need to subtract this base flow. Okay, or if they are trying to ask that yes, you need to compute the TRH, total runoff hydrograph, then you need to add DRH with base flow, because while you are subtracting the base flow, you are getting DRH. While you are adding the base flow with DRH, you are getting the TRH. That is a total runoff hydrograph. So sometimes you may get confused uh, while solving the problem. So keep these thing in your mind. Okay, so then again next question is also there. The problems is same, only thing is what it is asking, that time to peak or time of rising is. So time to peak, you already got the point, that at what hour, at what time peak have been noticed, peak time have been noticed. So you were getting a peak of 819, right? So what was it, what was the time? That is the question. So what is the time? Hello.
10
Time
hours.
10 hours.
10.
Yes, it will be a 10 hours. So yes, the thing is mentioned here, time to peak runoff is 10 hours. So this is a simple calculation for this question. I hope you all got these things.
Yes.
Okay, so I'm now just stopping this session because it's already 8:15. Though one problem is still got left. This numerical is basically related to more in solving the, like in generating the unit hydrograph. So we will be generating this instead of solving this problems. Means we have to directly make a plot of this. So that is the thing. Okay, just wait a minute. Okay, I hope you got the points. Sometimes what happen is that while I am solving, there may be like either in that question whatever we were solving, there may definitely there may be some mistake while writing, a question. uh, like if I compare watershed A and watershed B, from the picture itself you should have some logical thinking from your side, that just I mentioned that watershed characteristics would be same. So just I want to recall that length, whatever the LC and whatever the L value we are getting, it was too much drastic deviation was there, right? It was for watershed A it was coming 30, or maybe it was coming for LC it was 50, but in the other case for watershed B it was 130 or 100. So it is too much difference. So in that case I can't, we can't say that watershed characteristics are going same. Definitely there is some error in the question itself. A solution is, I guess a solution is more realistic one, but yes, question there may be some difference in that. I will try to see that question. Maybe I will in the next session I can address what could be the values, what will the clear values it should have. Okay.
One doubt, I do not know whether I missed the sixth one, time base of synthetic dimensionless SCS unit hydrographs. Uh, uh, did we cover in the assignment? I don't know whether I missed.
Which one? The dimensionless.
Yeah, SCS unit hydrographs.
So do I need to explain it again?
Please, if you can.
Yes, okay. So basically for SCS-CN dimensionless method, sorry, SCS dimensionless method only, for that case there is some hypothesis in the sense what, that it is assuming that the distribution of unit hydrograph will have a shape of triangular, like it will be a triangular shape initially. After making, after using the empirical equation that is mentioned in that method, we have to derive that triangle shape entirely. Then further they have added some corrections in the sense what, that we know that triangular will have a straight boundaries, right? But in general sense we always notice that the hydrograph will have a smooth curve. Okay, it will have a smooth curve. So in order to cut it out, the straightened part, there are some corrections which have been given, proposed, in order to smoothen that curve. So smoothness will be made further. Okay, I just want to present that question. So that question is a bit more simpler. Wait a minute. Yes, this was a question. Okay, so the question was for a basin of area 3 km square, time of concentration is, it is mentioned that TC is given. Okay, so here the question, in this question, sorry, wait a minute. Okay, ma'am, can you see this TC value?
Yeah, I'm seeing.
Okay, so TC is given here, how much? 1.25. Now triangular synthetic hydrograph, it is directly mentioned. So whenever we are seeing, we are looking into a direct triangular shape and we want to derive a synthetic hydrograph, then definitely you should have some idea directly that SCS dimensionless method assumes the triangular distribution of unit hydrograph. That is the thing. Then the question was asking about the time to peak or time of rising, it was asking. So how the approach was made? So you can see that SCS-CN dimensionless unit hydrograph. In this question, what was the additional thing that I just forgot to mention is that excess rainfall. This is also a unit hydrograph kind of thing. So ER, that is excess rainfall, will be a 1 centimeter only. Now remaining part, what we are doing is that we are deriving this formula that you can see here, TP equal to TR by 2 plus 0.6 TC. How we are deriving this? So you can see that from this hydrograph. Okay,
Yes, yes.
Can you tell me the TP value? What could be the TP value from this geometry itself? What could be the TP value? TP value should be how much? It should be somewhat TR by 2 plus TP, small TP, right? From the geometry you can
Yes,
see.
yes,
Got it?
yes.
Okay. Now going to this part, because see, this question does not have provided TP value directly. We don't have the TP value directly. Instead, what they have provided the TC, time of concentration. So so we need to look at into the relation between TP and TC. Then only we can get this value, na TP value. So relation between TP and TC is needed. So for that you can see this graph. This graph. Okay. Wait a minute. Why it is not erasing? Wait. I don't know why it is not erasing. Okay, just I'm adding to this. Wait. Can you see that this TP and TC representation?
Yes, yes. I'm able
Okay.
to see.
So yes, here this TP and TC relation is been developed. So for developing this, already there are certain already empirical relation have been developed in order to establish the relation between them. So TP is considered as a 60% of TC. It is a direct relation. 60% of TC is being considered. Okay. If you
Okay.
put 0.6 into TC, now you already have a value of TC, right? So this particular relation is taken to this part, TR by 2 plus TP. Now TR value you already have, that was 1 R, so 1 by 2. Then TP if you talk about, then 0.6 and into TC. So TC will be how much? Already mentioned that TC how much it was? 1.25. So it will be 0.5 plus 0.6 into 1.25 hours. That is simple. Ma'am, is it clear?
Okay, okay. It's clear. Thank you.
Okay.
Thank you.
Yeah, ma'am. Okay, I'm now stopping this presentation. Okay, then.
Thank you. Thank you very much.
Yeah, okay. Let me see. Bala Murugan have replied a lot. Okay, good Bala Murugan. You have almost answered everything, and that's good that you notice the things carefully. Ashish, well done. Ma'am,
Yes,
you are
yes.
also doing good. Okay, so we will meet in the next session. Ashish, you were also presenting something maybe in the next session.
Next session we'll present it.
Yeah, actually I will take it out some 10 minutes so that we all can have some idea from whatever you are doing. Okay?
Okay, okay, fine.
Yeah, good. Okay then,
Thank you.
goodbye
Thank you.
everyone. Yeah, bye.
Thank
Bye.
you. Bye.